And we are live, guys. Welcome back. That's my channel. Don't worry about it. Now, brain fart. Visual Studio. It's 10:30, so I don't think I'll be streaming for 1 hour. Update on close. Now, we were implementing lighting. We got our ambient lighting done, which is cool. I wanted to test it with a blender with a better texture. Monkey texture. Oh my god, this is horrible. Why can't I find a simple... Oh my god. Oh sweet Jesus. That's cursed. Come on. Unwrapping Suzanne. Yes, please. It's better or I can't. Probably need to paint it myself. Okay. No big deal. No big deal. No. New image. 512 by 512. Okay. Missing materials. Missing material. model by face. Texture paint. Okay, good. We have our monkey. Monkey! Oh, fantastic. Now. How can I save this? Open image. No, oh, yes, image. Save as Lucy, current working directory, textures. Monkey.png. Save image. We go to layout. We save. We have our monkey. Cool. And now white text. Kit monkey texture and white texture monkey texture. We create the monkey texture. Monkey by PNG. Let's go. And guys, we see our monkey. Fantastic. Oh my god. It's as ugly as they get. But for a test is good enough. Oh my god. Goodness gracious, what's yeah. So the light constants, let's check. Okay, if we go to the red, okay, our monkey is red, mostly red, mostly multicolor. If we go to the white one, we see basically the texture color. As we decrease the ambient strength, we sort of like, there is a very dark monkey, a very monkey in the dark. Okay, almost dark. Okay. Yeah, that's cool. Okay, so the ambient lighting works, kinda, or at least kinda works. So test ambient lighting with better monkey texture. Fantastic. Tac. And then okay. And lighting, basic lighting. Now we should really talk about diffuse lighting. Yeah, but we'll do it after the pause, after a little break. So that's it. Be right back. Okay. Break over. So diffuse lighting. That's what we want to achieve tonight. Hopefully. I don't think we'll be able to pull it off tonight because I started late. But still something. So diffuse lighting. Now, ambient lighting by itself doesn't produce the most interesting results because it's just a flat color at the end of the day. But diffuse lighting, however, will start to give a significant visual impact on the object. Diffuse lighting gives the object more brightness the closer its fragments are aligned to the light rays from a light source. Okay, this light bulb is the light source. To give you a better understanding of diffuse lighting, take a look at the following image. Okay. To the left, we find a light source with a light ray targeted at a single fragment of our object, this. We need to measure at what angle the light ray touches the fragment. If the light ray is perpendicular to the object's surface, the light ray has the greatest impact. To measure the angle between the light ray and the fragment, we use something called a normal vector. That is a vector perpendicular to the fragment's surface, here depicted as a yellow arrow, the normal. That's a vector. We'll get to that later, okay? The angle between the two vectors can then easily be calculated with the dot product. Yes, a little like thingy. If you think about the light ray, you're probably thinking about this sort of thing. But if you want to get this angle, you need to take this vector. Okay, so it's not like the light ray per se. It's not the direction of the light. It's not the light ray. It's the opposite of the light ray. Then you do the dot product, and with the dot product you find this angle, or the cosine of that angle. You also need to normalize this d vector and this n vector in order to just have the cosine, in order for the dot product between these two vectors to just be the cosine of that theta angle. Anyway, to measure the angle between the light ray and the fragment, we use something called an okay. You may remember from the transformation chapter that the lower the angle between two unit vectors, the more the dot product is inclined towards a value of 1. Of course, it's the cosine of an angle. Cosine of 0 is 1. Okay? Cosine of 90 degrees is 0. Okay? When the angle between the vector is 90 degrees, the dot product is 0. Yeah, okay. The same applies to theta. The larger theta becomes, the less of an impact the light should have on the fragment's color. Of course. When this theta is 0, then the light ray is basically parallel to the normal. So it shines the brightest on the fragment. The more the theta increases, the less it shines, until you have the maximum theta with 90 degrees. So with 0, everything that is that lies, so here you have positive 90, here you have negative 90, but that's 0 nonetheless. That's 0 nonetheless. The result, the cosine of something that goes from from plus 90 to negative 90 degrees, it's always positive, so we don't have a problem of sign. The problem is that everything past positive 90 and negative 90, that's basically, that would be something of this kind. Okay, sorry, everything like this, okay, would result in a negative value, and it also wouldn't make sense because you are going through the object. Okay, so that's it basically. To measure the angle, okay. Note that to get only the cosine, we need to work with unit vectors. Yes. So normalized, of course. The resulting dot product then returns a scalar that we can use to calculate the light's impact on the fragment's color. From 0 to 1 it's perfect. Resulting in differently lit fragments based on their orientation towards the light. So for the diffuse lighting we need the normal vector that is perpendicular to the vertex surface, the directed light ray, a direction vector that is the difference vector between the light's position and the fragment's position. So to calculate this light ray we need the light's position vector and the fragment's so we need the light's position vector and the fragment's position vector. In our case, since we are doing directional lights, we'll have basically just the light direction. Normal vectors. Okay, the normal vector will have the normal vector for the light direction. We just explicitly, if we were to implement, say, something like a point light, spotlight, or whatever, we would have like the position of the light. Okay. We are implementing a directional light. We just have the direction. Normal vector is a unit vector that is perpendicular to the surface. Okay. We can use the later to calculate the normal vectors for all the cube's vertices by using the cross product. You can see add them to okay. Work. Not a big deal, but we have to handle the normals. Vertex shader input, position, let's call it float 3 normal, it's fantastic, normal, it's better. The position, the float 3 normal. Okay. The default vertex shader, the output dot normal equals the input dot normal. Here in the default, here in the unlit pixel shader, we do nothing for now. With the lit pixel shader, we'll do something with the normal. Now in the main, if we try to do something, shit will break. I'm calling input layout break. Error. ID3D11 device create input layout. The provided input signature expects to read an element with semantic index normal 0, but the declaration doesn't provide a matching name. Okay, so oops, 1, to step back here. Position, oops, normal. R32, G32, B32, float. Let me check the input element desk. First, second, third, fourth. First, second, third, fourth input slot. Okay. An integer value that identifies the input assembler. Valid values are between 0, 1, 2. Wait to like need to check the meshes. CPU mesh, vertex count, index and positions, normals, UVs and indices, okay. And when we do the import, read the vertex data, read the index data, positions, normals, I say mesh normals I dot x y z vertices and faces. So if I try to do it now, access violation, access meshes, the thing is that I need to export again. So this is a file export obj meshes. This will be monkey. Selected only. Triangulate mesh. No materials. And export. With the axis thingy. File export obj. We do the leaf superset. We export the normals, the colors, triangulate the mesh, axis base, and we export, and everything should be fine. Everything is not fine. So model normals is empty. Why? problem here is that the model.normals hasn't been okay, let's do it again. Okay, oh my god, what happened? Something ain't right, guys. Something ain't right. So the model vertex count, the normals, okay, in the CPU mesh. Okay. What about the GPU mesh? The GPU mesh, we need the normals, vertex buffers, position, normals, UVs, so it's 3, and here we just from GPU mesh, here we do the positions, here we'll be doing the normals, so this subras data mesh dot normals. Oh my god, that's quite messy. Mesh positions, mesh normals, vertex buffers 1, vertex buffer strides 1, vertex buffer offsets, okay. UVs, this is 2, pardon, 2 and 2. These should be handled, we should be able to handle this in a better way, come on. This is absurd. Programmatic way. If we do this, oh my god, so everything has been fixed. Fantastic. That's just fantastic. Okay, so here we basically what I would love to do is just loop through all the vertex attributes and run the same code basically, and then create on the side the buffer for the indices. Load the normals, add normals, add support for mesh normals, and now we just want to the diffuse color, but it's getting late. We need the light constants. We need the ambient color, the ambient strength, and the light, direction, basically. So I think everything is fine. Strangely, I'm surprised, but GPU mesh, loading when building it from a CPU mesh, everything is cool. We just do the vertex buffers 0, vertex buffer 1s, that's the normals, that's the positions, normals, UVs. Set vertex buffers. The starter slot is 0. The non-buffers is the vertex buffers count. Vertex buffers strides, vertex buffer offsets. And in our vertex buffers, basically, do it like that. The first buffer is the positions, which makes sense. First position. Then you get the normals, and then you get we have set up the normals, which is a little bit of grunt work, and we also like made our little monkey mesh, which is cool. Better test than flat white, of course, way better. What we want now is to implement our properly implementing our like the diffuse color. Oh, not this thing. Fantastic. Lightcasters with the directional light. Okay, so implementing our directional light with the basically the diffuse lighting. So that's it for us. But at this point we'll do it later because it has already been 1 hour. Oh my god. Did not notice that. Okay. Like, getting a little bit tired. I think I'll go to sleep. Thank you for tuning in, and no one tuned in. But yes, I hope someone someday will be like binging this and saying, oh, like look at the beginning, it was so shitty, he had like 2 models, very clunky RTS camera, everything looked like shit, but he still did it. So yes, I'm basically streaming for like documenting the project, and also for like training myself into speaking while I code, explaining, like motivating the things I do, and also like sometimes actually